In this video, we are going to discuss about data augmentation. So what is data augmentation? It is a strategy that enables practitioners to significantly increase the diversity of data available for training models without actually collecting new data. So these techniques include cropping, padding, flipping, right? So these are the common techniques that are used to train large neural networks. So it is used to increase the accuracy and learning of the model. So when we talk about data augmentation, this can be used to artificially expand the size of a training data set by creating modified versions of images in the data set. Training deep learning neural network models on more data can result in more skillful models, and the augmentation techniques can create variations of the images that can improve the of the fit models to generalize what they have learned to new images. So what is the use of this data augmentation, right? So we all know that deep learning is better if we have a large data set, right? So this is used to expand the training data set in order to improve the performance and ability of the model to generalize. So the performance of the deep learning neural network improves with the amount of available data. So image data augmentation is the most well-known type of data augmentation, and it involves creating transformed versions of images in the training data set that belong to the same class as the original image. It transforms the range of operations like image manipulation, such as shift, flips, zooms, and there are many such options, right? So here, what is our intent? It is to expand the training data set with new examples. For example, a horizontal flip of a picture of a cat may make sense because the photo could have been taken from the left or right. A vertical flip of the photo of a cat does not make sense and would probably not be appropriate given that the model is very unlikely to see a photo of an upside down cat. So it is clear that the choice of a specific data augmentation techniques used for training data set must be chosen carefully, and within it should be chosen carefully that we have to see it, right? So you can get some idea about data augmentation from this picture. So this is the original image, and these are the augmented images. So you can see some data augmentation techniques over here, right? So you can see these are the original, and here it is rotated, and here it is blurred, and here you can see contrast feature, here scaling, illumination, and projective. So here what I'm trying to say is, like, here I have taken some images and just I'm showing what are the possible augmentation techniques, right? So this is what we are going to understand in this session in detail, right? So the first one, what we are going to see here is about horizontal and vertical shift augmentation. So generally a shift to an image means we move all the pixels of the image in one direction. It could be horizontal or vertical, but we keep the image dimensions the same. This means that some of the pixels will be clipped off the image, and there will be a region of the image where new pixel values will have to be specified. So the width shift range and height shift range arguments to the constructor that controls the amount of horizontal and vertical shift. So here you can see that this scenario is important for network. So this is basically to remove biasness of assuming certain features of the object, right? Now the second technique what we are going to see is about rotations, right? So here the network has to recognize the object present in, like, here you can see that the image is rotated at 90 degree. It will not add any background noise in the image. If you see here, you can see that 45-degree rotation, right? So there could be some background noise. So a rotation augmentation randomly rotates the image clockwise by a given number of degrees from 0 to 360. So the rotation will likely rotate pixels out of the image frame and leave areas of the frame with no pixel data that must be filled in. Now the next one is about scaling. So the image can be scaled outward or inward. So while scaling outward, the final image size will be larger than the original size, right? So I think this is the base image and you can understand from this, right? So the scaling, when we do scaling, the image, the scaled image size is larger than the original image. So the next one is about cropping, but these all things we might have done when we take photos in our phones, right? In our smartphones, basically, right? So what do we do whenever we want to keep DP for us, like in the WhatsApp, like we used to crop the pictures, right? So here the cropping means, like unlike scaling, we just randomly sample a section from the original image. We can then resize the section to the original size, right? So the same meaning only, right? So the next one is about jitter. So you can understand about this jitter, like here we can see two stuffs. One is about simple and the another one is about complex. So simple means it is randomly jitter contrast, right? And complex, we can apply PCA to all red, green, blue pixels on training set and sample a color offset along principal component directions and add offset to all pixels of a training image. And not only these kind of techniques, actually what we have discussed is very less, right? So also we can do a random brightness augmentation. So here we maybe or we can augment it either by randomly darkening images, brightening images, or both. And then the intent is to allow a model to generalize across images trained on different lighting levels. And this can be easily achieved, right? Fine. So that we can do. And then we can also do zoom augmentation. So it may zoom the image in and either add new pixel values around the image or interpolates pixel values, right? And also we can do some other techniques like translation, rotation, stretching, shearing, and lens distortions, right? Okay. So how do we do this data augmentation? So training, like add random noise, and testing will marginalize over noise. Then we do image augmentation. It artificially creates training images through different ways of processing or combination of multiple processing like shifts, rotations, shear, and flips. And it is very easy to implement and it gives very good results, especially on small data sets, because we can see whenever we use deep learning techniques, if you use small data sets, that's not really going to be great, right? So that's the reason we do such kind of techniques during training, so that when you do such kind of a training, definitely the data set become larger, right? So that we can get a very good performance, right? It can easily fits into framework of noise or marginalization, right? So hope this is really clear to you, right? Okay, thank you.